Right. Right. So, good morning, all. So, good morning, all. So, welcome to this one-day workshop on simulation tools for nuclear physics. So, we'll be dealing simulation tools related to the fourth semester single major UG physics. The UG physics, if I go through the syllabus, so if I go through the syllabus, that nuclear physics comes in fourth semester of UG single major physics. So, introduction to nuclear and particle physics. So, in theory, you have 5 units. First 2 units are related to first unit is related to nuclear properties. Second unit is elementary particles. Third unit nuclear reactions. Fourth unit deals with nuclear decays, and fourth unit also contains nuclear accelerators, particle accelerators. Fifth unit deals with applications of nuclear and particle physics. So both medical applications and physics, astrophysics applications are there in that. And coming to the laboratory session, 6 or 7 experiments basically are related to GM counter. With this single equipment, people have planned 7 experiments using that single equipment. But still, I mean, if you go for sorry, I need to share my screen. Okay, so these are the 5 units in the theory. So properties of nucleus, elementary particles, nuclear reactions, and nuclear detectors is third unit. Fourth unit is nuclear decay and nuclear accelerators. Fifth unit is applications of nuclear physics and particle physics. And coming to lab session, all the 6 or 7 experiments are linked with GM counter, a single equipment. But still, I mean, because other equipment are not accessible to college level, like these particle accelerators, all these things are not accessible for college level teaching. So that is why this session, this workshop is planned using the simulation tools for nuclear physics. So we'll start with a more convenient one. The first one is I'll start with cyclotron, a particle accelerator. Okay. The first tool I'm going to deal with is a cyclotron. Right. So you'll come across this in our fourth unit. So cyclotron is basically a particle accelerator where you'll be accelerating charged particles. So when you apply electric field to charged particle, the particle will be accelerated in the direction of electric field. Right? So when you apply electric field, let's say along x-axis, the particle will be accelerated along x-axis. Right? But if you want to accelerate the particle to very high velocities, then we require miles and miles of length electric field. So that is what it is used in linear accelerator. Probably it is in Germany. Linear. Okay, it is of 2 miles length electric field. Is used to accelerate particles. But that is also not sufficient for the kind of experiments we are doing now. So it requires even more higher energies, higher accelerations. So to control the particle or to accelerate the particle further velocities, we require, I mean, we use magnetic field so that we divert the particle into a circular motion. So when any charged particle moves in a perpendicular magnetic field, it executes circular motion. Okay, so the particle executes circular motion in presence of magnetic field. So if you see the manual and the equations for that. So when you apply magnetic field, what happens? The charged particle moves in a circular motion. Here the velocity remains constant. I mean, we should call it as speed. Speed of the particle remains constant. Since the direction changes, we can call it as acceleration. So the magnitude of the velocity remains constant. the direction of velocity is changing in a circular path. So in the presence of magnetic field, perpendicular magnetic field, the particle undergoes circular motion. So it is also a kind of acceleration with constant magnitude of velocity. Okay. So what we are doing here is we are applying electric field. So there are two D-shaped metal drums here, and they are connected to electric field. So on one side you have positive potential, on the other side you have negative potential. The charged particle starts its journey in the middle of the two D-shaped drums. So it gets accelerated by the electric field first of all, and it gains some velocity. Once it enters the drum, electric field effect will be cancelled. I mean, you have only one kind of field here, so the particle will move with uniform velocity. I mean, the acceleration part will be only in between these two drums. Further, the particle enters the other drum. It will move with uniform velocity. So, if at all, if you want to accelerate it, we have to apply electric field and we have to go on miles and miles of distance. Instead of that, we are turning the particle, keeping its speed constant and bringing it back using magnetic field. Instead of creating a miles and miles of length of track of electric field, we are turning the particle and bringing it back to the same electric field location. Okay. So after taking a circular motion, again it enters into the space between the two drums. Again, it will get accelerated by the electric field. Further, once it enters the second drum, it just keeps the velocity by using magnetic field and takes a turn. And in between the two drums, again it will get accelerated. So if there is no electric field, the particle will just keep on moving in a same circle. Just because of the electric field in between the drums, after execution of a single cycle, the particle will go to higher radius, higher orbit. So, so if you see the simulation, see the particle at the end of each cycle will go to higher radius just because of the electric field. So the process continues. And once it reaches the maximum level, so once it reaches the maximum level, the particle will emit out of the drums. It will come out of the cyclotron. So what are the control parameters? Who is controlling the maximum speed or maximum velocity of this charged particle? Is it the electric field or magnetic field? Magnetic field just keeps its velocity. Acceleration is given by electric field only. So we'll confirm that whether change in magnetic field controlling the velocity or change in electric field controlling the velocity is a matter of discussion. Okay, so I'm keeping so here for 2000 volts of electric field potential and 0.2 Tesla of magnetic field. The frequency is constant, 3.05 megahertz. Let's say I will confirm that whether it is changing or not. So frequency is remaining constant. What is frequency? What is the frequency of electric field? I mean, why should we change the electric field sign? Why do we need to change it? So let's say the charged particle here I am considering is proton, a positive charged particle. So to accelerate it, I need to apply negative potential to the left side drum. Okay. So the particle will enter the left side drum, and once it completes the journey inside the left side drum and exits the left drum, by the time what happens? By the time still this right side drum is negative, it will get repelled. But to continue its journey, we have to switch it to positive potential, right? So we require a frequency, which is controlled by magnetic field. Velocity of the particle inside the drum is controlled by magnetic field. So the electric field frequency should be matching with the magnetic field. So if you see the equation, what is that equation? The frequency of QB by 2 pi m. Just depends on the magnetic field. If the magnetic field strength is very high, the particle will come out of the drum quickly. So we have to switch the electric field quickly. So more the magnetic field, more the frequency of electric field required. Okay. So that is how the frequency is controlled. So here frequency is constant, kinetic energy is increasing continuously, speed is also increasing continuously as a function of time. So I'm keeping electric field strength constant, magnetic field strength also constant. So but the maximum velocity that it can acquire is what? So in this for this setup, so that is why we are using speed instead of velocity. In the presence of magnetic field, speed remains constant, velocity changes because direction is changing. So as a whole vector, magnitude is constant, direction is changing. So it is considered as acceleration. Velocity is changing as a function of time, but speed is constant. Magnitude of velocity is constant. So speed is 3.71 into 10 power 8 meters. It is 10 power 6 meters per second. Okay, 3.7 into 10 power 6 meters per second. What is speed of light? 3 into 10 power 8 meters per second. Right? So that means what? 300 into 10 power 6 meters per second is the velocity of light. So what is the relativistic limit? The particle is approaching the relativistic velocities on a condition. What velocity is considered as relativistic limit? What is the minimum velocity? So when you are dealing with numbers, let's say from 0 to 1, and when you try to round off any number less than 0.5 is considered as 0, and any number above 0.5 is considered as 1. Right? The same rule applies here also. If the velocity of the particle is less than 1.5 into 10 power 8, it is considered as non-relativistic. If it is above 1.5 into 10 power 8 meters per second, the velocity is considered as relativistic velocity. So more than half of the velocity of light is considered as relativistic limit. So here the particle is still in non-relativistic limit. So if it goes beyond that, like 1.5 means what? Around 150. We'll see that. So it is 3.71. So I'll raise the magnetic field. Instead of 0.2, I go for 0.3. What was the speed earlier? 3.17. So now it is more than 5. 5.6. 5.6 into 10 power 6 meters per second. So how come magnetic field is controlling velocity, controlling the speed? Actually, what we are discussing as of now, the electric field is the only control parameter that controls the acceleration of the particle. Magnetic field is just bringing back the particle, keeping the speed constant. Then why magnetic field is rising the speed? And if I keep the magnetic field same as that 0.2, let's say I keep the magnetic field 0.2 and rise the electric field. Actually, now it should rise. But our rule breaks now. You'll get again 3.17. Whatever that number you got earlier for 0.2 magnetic field, 3.71. You got the same number. So how come? Our fundamental basic understanding of the concept is completely broken. So to our understanding, what is going on? Electric field is the only field that controls the acceleration, and magnetic field is just keeping the velocity. But here, magnetic field is rising the velocity, and the electric field is not at all changing the effect. I mean, final velocity. Where is the problem then? So the problem is electric field controls the speed only when the particle comes in between the D's. So electric field controls the speed only when the number of turns are increasing. So let's say if there is a number of turns are increasing. So here how many turns, how many times the particle is coming in between the D's? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, around 11 or 12 times. So if I reduce the magnetic field, so if I raise the magnetic field, what happens? If I raise the magnetic field, velocity is constant. So the particle revolves in a low radius orbit because velocity is already decided by electric field. So here velocity is constant. So if I raise the magnetic field, particle revolves in a low radius orbit. So that can be confirmed. So if I raise the magnetic field, what happens? Particle revolves in a low radius orbit. In the previous case for 0.2, we have seen 11 rotations. Now it is more than 20 probably. So see, the sign is changing, plus and minus. So when right. So now how many turns? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Almost 27 or 28. So that is why speed is now 5.56. So electric field controls acceleration, but only when the particle enters the region between the D's. So in the earlier case, the particle entered 11 times. Now it is 27 times. That is why speed has increased. So now tell me who is controlling the speed. How? If you raise the magnetic field, it is ensuring the particle remains in the D's, remains in the cyclotron for more time, or it takes more number of terms. Okay, so it is the electric field responsible for acceleration, but the number of times the particle come across the electric field is controlled by magnetic field. So that is why with the rise in magnetic field, we are able to get more velocity, and electric field is playing no role actually in this case. So now we go for relativistic case. Means I can raise the electric field more and more. I can raise the magnetic field also to more and more. Earlier it was 0.2, now it is 10 times more. So what happens? Initially the frequency remains constant. So what is the frequency here? It depends on the magnetic field, which we are keeping constant. It depends on the charge of the particle, that is also constant. It depends on mass of the particle, which is constant in non-relativistic limits. So when we go to relativistic limit, that also changes. So the frequency is now velocity dependent. There is a velocity term in frequency. So we have to adjust the frequency continuously as the velocity rises. Otherwise, the particle will collapse. Right? Frequency is increasing continuously as the mass increases, as the speed increases. So we have to adjust tune the frequency also continuously as the particle speed rises more and more. So that is what we will see here. So focus on that frequency number. Earlier the frequency was constant. So to some extent the frequency remains constant around 30s, and once the particle speed reaches the relativistic limit, relativistic limit means what? More than 150. The frequency, so particle becomes heavier and heavier if the speed increases. So if the heaviness increases, frequency should reduce. Right? So now the speed is 90 into 10 power 6, around 100 times 10 power 6. So 30% of speed of light. Right? So if I raise the magnetic field further, let's say 3, you may even go to that relativistic limit. So that is how you have to alter the frequency. So do we need to raise the frequency or reduce the frequency? Check the equation. Every time you must ensure, every time your equation should speak for you. So here the frequency is inversely proportional to mass of the particle. So when the particle speed increases, mass increases. So when mass increases, frequency should reduce. So when the mass increases, particle moves slowly. Why? Magnetic field is proportional to velocity and proportional to mass. So numerator increases, otherwise the particle revolves in a lower radius orbit again. So if you don't change the frequency, check what happens. If you don't change the frequency, I'm not adjusting frequency, relativistic limit without frequency adjustment. So I'm keeping the frequency constant. Actually, with the rise in mass, frequency should reduce, but I'm keeping it higher value. What happens? So up to non-relativistic limit, particle rises its acceleration, it goes on to higher and higher orbits. Once it reaches the relativistic limit, now the frequency is not supporting. Particle goes back to lower and lower radius. Check the radius. It again comes back, traces back to lower radiuses. Stops there. Check the speed. It is reducing. It is going back to lower and lower orbits because the frequency is mismatching. Frequency is very high. And finally, the particle collapses into the original location. Dead. So with the rise in mass, or when you approach the relativistic limits, you have to reduce the frequency. Is that clear? So you can record this entire process. If you are using your mobiles, there is a AZ screen recorder app. You can record the entire process, all those numbers. I mean, to plot a graph at least. You can plot a graph between frequency and speed. With the rise in speed, frequency reduces. That can be studied in the relativistic case. And with the rise in magnetic field, the velocity of the particle increases. That can be studied in non-relativistic case. Okay, so you can plot the graph. I mean, if you are using desktop, there is an app for Chrome, Screencastify, Chrome extension. There is a Chrome plugin called Screencastify, which records the videos or the screen. You can add it to Chrome. So the entire session is recording. I mean, you can see it later if you want. Yeah. So where is my so enable mic and webcam. I mean, if you want, you can. Camera is already in use. Okay. So Screencastify. You can pin it to your taskbar. It comes here. Okay. Reset. I'm going to relativistic with frequency adjustment. So we have to sign in. So whatever you record, it will be stored in your drive. Right? So once you register and log in, you'll get its options, screen recording. Okay, you can record your screen. This tab. So what happens? So starts recording. You can even add your video and audio. Right. Once it is done, you can stop recording, pause, end recording. So free version can store only 10 videos. Right. So you can play your video, pause wherever you need, and record your data. Right. So then for the first part, for the first experiment, cyclotron, you can plot a graph between velocity, strength of the magnetic field versus velocity. Sorry. Okay, frequency remains constant. Okay, strength of the magnetic field and final velocity attained. So for the non-relativistic case, no problem. Video record. Okay. Link పంపించారా? పంపించారు. Yeah, ఇదేనండి. if you are using your mobile phone, you may use this AZ screen recorder app. AZ recorder. This is the app on your mobile phone. Okay. So in the non-relativistic case, you may go up to 0.3 probably, 0.5. So maximum is 0.4 magnetic field in non-relativistic case. So you may start from 0.1, 0.2, 0.3, 0.4, 0.1, 0.15. So you may start with B max. So 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4 is the maximum. I mean, if you go for so maximum is 0.4 in non-relativistic case. Okay. Turn on this. So this is the lab manual text with units and aim, apparatus, formula, table, and all those details. Like so, for cyclotron, you have aim, apparatus, formula, procedure, observations, results, and precautions. And for synchro cyclotron, you have to adjust the frequency. So the corresponding equations are there. For frequency adjusted cyclotron, synchrotron. So your frequency is now velocity dependent. So as a rise in velocity, mass increases and frequency reduces. That can be verified. So this is the lab manual text I have pasted in the chat box. And then for non-relativistic case, you have to study the variation of maximum velocity as a function of magnetic field. So here the maximum limit is 0.4 Tesla. So starting from 0, 0.5 up to 0.4. When it is 0, velocity is 0. So when it is B is 0, velocity is 0. And when you rise the magnetic field, you'll get some velocity, maximum velocity. So you can plot a graph between V versus V maximum. So whenever you plot a graph, independent variable should be on x-axis and dependent variable should be on y-axis. The variable that is under user control should be on x-axis. So the magnetic field is in user control. So magnetic field x-axis lo teesukovali. The one that depends on magnetic field, here it is maximum velocity, that should be on y-axis. Okay, so this is one study in non-relativistic case, and as a function of electric field, Vmax remains constant. That also can be verified. And when you go to relativistic case, you have to record the entire process using screen castify if you are using desktop, and AZ screen recorder if you are using your mobile phone. And there you have to record the instantaneous velocity and frequency. How frequency changes as a function of velocity. So here in this case, velocity is an independent variable. Frequency depends on velocity. So the graph will contain V instant along x-axis and frequency along y-axis. So with the rise in frequency and with the rise in velocity, frequency reduces. That can be verified. And in the relativistic case also, you can study this as a function of magnetic field, maximum velocity increases. That also can be studied. Okay. So that's about cyclotron. And our next experiment is what? GM counter. GM counter simulation. So there are so many tools. The Samrita VLab tool is not ready yet. So they have developed only this manual theory and all are ready, but virtual lab is not developed yet, probably, for this GM counter experiment. So other one, physics lens. This is more simplified version. So I'm going for the second one, gigaphysics. So you can search for that on your mobile phone also. GM counter simulation. And I'm using the second link, gigaphysics.com. Gigaphysics.com, second link. Giger Muller Tube Virtual Lab. Yes. So here you have a user manual and a lab guide. All the material is provided there. So 2 experiments can be done using this simulation. So there links are provided for lab guide for identifying the half-life of barium 137. Another is identifying the unknown radiation. These are the 2 experiments that you can perform using this simulation. Okay. So let us explore what are the options available here. So there is a counter and timer, radiation source. So this is the radiation source and this is the detector or counter. So this is the counter. So when you add a radiation source like alpha particle source, beta particle source, gamma particle source are unknown. Anything can be added. So I'm taking alpha particle source as the first step. Alpha particle source, and this is the detector. The top portion cylinder is the detector. And you can see the counts here in the display. Okay, I'm placing an alpha particle source and you can verify the penetration depth. Like if you place a cardboard, lead block, plastic sheet, and you can put number of those barriers, 1 barrier, 2 barriers, they all can be modified. So if you place a lead block on the way of alpha particles, I mean in the absence of them, particle counts will be different. So you can set the count, let's say for 10 seconds, 30 seconds and 1 minute. 3 stages are there. So this timer will run automatically. And you got the count for 30 seconds, let's say. This also you can record using Screencastify and plot a graph as a function of time. So as a function of time, how many counts are recording can be verified if you record the entire process. So after 30 seconds, counter will stop. Timer may run. This timer may run, but counter will stop after 30 seconds. So even if you start lately, I mean, the clock will run automatically. So once you begin the clock, it will start running. But counter will take, counter is controlled by this setting. So when you are setting 30 seconds and your counting starts at, let's say here 15. So the counter will run up to 45 seconds. Okay, the countings, now I have started at 15 seconds and I set the counter for 30 seconds. So it will stop counting after 45 seconds. I'm starting after 15 seconds. From 15, I have to go till 30 seconds. So counter stops at 45. Done. The timer will run, but counter will stop. The counter setting is controlled by this last one. either 10 seconds, 30 seconds, or 1 minute. So you can keep 1 minute timer and plot whatever. So now as a function of number of barriers, you can verify this. So now I'm keeping lead block, one lead block, same 30 seconds. Okay. So when I keep one lead block, it's reducing enormously. Earlier it was around 600. Right? So you got 31 count for 30 seconds. So if you raise the number of blocks, so I started at around 50. From there, 30 means 80. So 1 minute, 20 seconds. 1 minute, 25 seconds probably. So am I recording the session? It's recording. It's around so what happened? Is there any change? Right. So thickness of the block has a minimal effect, but there is a drastic effect once you introduce one block at least. Okay, you can study this. First of all, if you record the first possibility for this setup, first possibility, recording the decay. Let's say, I mean, you can even study the of this barium atom. So half-life of barium atom can be studied. I mean, as a function of time, how many disintegrations you are recording can be studied. So if you record the data for let's say 30 seconds or 1 minute, whatever. Right now, this you can use to study the half-life. As a function of time, how many disintegrations are taking place. So that you will see there is a program. So here you can study the number of counts as a function of time. That is one study, even for alpha particle, beta particle, or gamma particle. Number of counts as a function of time. Study number one. Second one, number of counts as a function of number of blocks. If you raise the number of blocks 1, 2, 3, 4, 5, you can plot it. How many number of counts? So as on x-axis you will take number of blocks, and on y-axis you will take the count. Study number 2. Study number 3, half-life period of barium atoms. So if you collect data for number of disintegrations as a function of time, you can plot a graph and check the half-life period. Right. So this part is over. So till now, 3 experiments. GM counter. I mean, everything on GM counter can be in one record. Cyclotron, one record. Synchrocyclotron, third experiment. Next one, I'll go to simulation tools using MATLAB or Octave. Okay, so I'll go for half-life of radioactive half-life. So I'm sharing the link. The earlier links, this cyclotron link also I'm sharing. Cyclotron and GM counter. These are all over. Now I'm going for half-life period calculation using MATLAB code. MATLAB or Octave. I'm using Octave, which is a free version for MATLAB. So here, to simulate the radioactive decay and determine half-life of radioactive substance using GNU Octave. So that is the experiment I'm considering here. So we need GNU Octave. So there is an online compiler. Search for Octave online. Octave online. And take the second link. mycompiler.io. Search for Octave online. Octave online. Online Octave. And take the second link. mycompiler.io. Click on that. Run your Octave or MATLAB code. So here the instructions are very simple. All those mathematical equations and functions can be directly here. Let's say the simple function of plotting a graph between 0 to 2 pi, let's say, of sin x or cos x. You can write any program, and if you click on run, you'll get the output. So you got the graph for cos x from 0 to 2 pi. So pi is a built-in function for value pi. So I'm taking x value starting from 0 with a step size of 0.1 up to 2 pi. So that is, and I'm plotting x versus cos x. I mean, this is a sample program. I'll share the actual program also. So the actual program is here. WhatsApp. So I'm sharing it on WhatsApp now. So this is the program. WhatsApp. I shared it on WhatsApp. So you can just copy paste it into your online compiler. I've shared the program on WhatsApp. Just copy paste the program into your online compiler. తీసుకున్న values కోసం let click on green one function తీసుకున్నాను okay cos x cos 360 means single point, so you have to plot between x versus cos x. Right, so I shared the program, radioactive half-life simulation on Octave. So you can copy paste into your online compiler. So remove the existing sample code and paste it into your online compiler. So every parameter is explained in the code. So what I'm trying here is I'm trying to implement this equation. The radioactive decay equation is given by n is equal to n naught e power minus lambda t. Lambda is the decay constant, n naught is the initial number of atoms, and t is the time. N is the number of atoms remained after decay at that particular time. So what are all the inputs I need? N naught is an input, lambda decay constant is an input, and I have to vary time from 0 to some particular number, and I have to count the number of particles remaining. So that is what the code says directly. So I'm starting with n naught, 1000 particles, initial number of radioactive nuclei. Explanation is also given there. So whatever you write after percentage symbol will be considered as comment in the program. So any text after percentage symbol will not affect the program. That is, they are just comments for our understanding. So n naught I'm taking 1000, lambda value 0.01, maximum time is 10,000 seconds. Maximum time is 10,000 seconds. Code వచ్చిందండి, program వచ్చిందా? Sure. వాళ్ళకి పంపించారు. Program WhatsApp లో పంపించారు. Okay, so maximum time I'm considering here is 10,000 seconds. Time interval 10 seconds. So time variable here is that t starts from 0 with a step size of dt up to t maximum. So just like earlier what we have seen, x starts from 0 with a step size of 0.1 up to 2 pi. Here I'm taking t starts from 0 with a step size of dt going up to t maximum 10,000. And I'm writing all the equations. N is equal to n naught e power minus lambda t. I have defined lambda, n naught, t. Everything is defined here. And I'm defining t half also, which is log 2 by lambda. Now I have to draw a graph between t versus n. So whatever values that t takes, n also will be calculated for all those values. Like 10,000 values of t are there. You get 10,000 values for n. You'll get a graph, and these are the additional decoration parameters for graph. R stands for red color, and line graph, and line width is 2. And I'm marking two other lines, one for t half, another for n naught by 2. So if you run the program, you can see. So x-axis time, y-axis number of particles, number of nuclei remaining. So this is the graph n versus t versus n. Graph for t versus n, that is red in color, a line graph with line width 2. Those are the settings I have made, and I am marking along x-axis t half I am marking, and along y-axis number of particles at t half, n t half is also marking. So for that, what I am doing here, I am marking the coordinates. So the first data set is x coordinates, second data set is y coordinates. I'm plotting a line. So first data set is x coordinates, second set is y coordinates. So it is t half comma 0 is my first coordinate. T half comma 0 is my first coordinate. So I'll place a dot at t half around 2000 and y value is 0. So t half comma 0 is my first coordinate in this data, line number 22. So the first set is x data, second set is y data. So t half is x data, 0 n naught is y data. So first coordinate is what? x1 y1 is t half comma 0. Second coordinate is t half comma n naught. So I'll get a line from t half comma 0 to t half comma n naught. You get a vertical line. T half comma 0, t half comma n naught. You get a vertical line. And for horizontal line, I'm taking 0 t max as x data, n naught by 2, n naught by 2 as y data. So what do I get? I'll get a point at 0 comma n naught by 2, 0 comma n naught by 2. N naught is 1000, so n naught by 2 is 500. So I'll get a point at 0 comma n naught by 2, x value is 0, y value n naught by 2. Second point, t max comma n naught by 2. So other end you have t max comma n naught by 2. So this is just to identify the location of t half and n half, n naught half. So I plot those two lines. So with that, and I'm also printing the value of theoretical half-life, which is t half. So the output of the program is theoretical half-life, whatever number you got, 693 seconds. Okay. And the graph. So from the earlier simulation, so is this clear? So you are entering the value of time constant, whatever lambda value, and n naught number of initial number of particles. Sorry, n naught and lambda by 2. Sorry, n naught and lambda. These are the initial conditions you are entering, and you wrote the equation, and whatever two equations are there, n is equal to n naught e power minus lambda t, and t half is equal to log 2 by lambda, and we have plotted it. T half is printed, t comma n is plotted. That I'll tell now. So here equation is calculating, we are giving values of t and n value is getting calculated. But in our simulation, what do we have? T versus n. We got a graph for t versus n. So there we have to identify these t half and all those things from the graph. So we have to make small modifications to this program. So I'll modify it and share it again. So what are all the modifications that we need? We are not using equations now. And we don't know also these values. The number of atoms decayed. So you have to count the number of atoms remaining. So you have to fix some n naught over there in that experiment, in that data. N naught to fix chesi, whatever values counts you are getting should be subtracted to get the number of atoms remaining. మనం ఇక్కడ ప్లాట్ చేసేది ఏంటంటే నెంబర్ ఆఫ్ ఐటమ్స్ రిమైనింగ్ కి ప్లాట్ చేస్తున్నాం యాజ్ ఎ ఫంక్షన్ ఆఫ్ టైం. అక్కడ కౌంట్ చేస్తుంది ఏంటి నెంబర్ ఆఫ్ ఐటమ్స్ డికేడ్. సో వీ హావ్ టు ఫిక్స్ సమ్ maximum number of atoms and subtract the count in the simulator. Then you get number of atoms remaining. Okay. So T also I have to take an array. So T is equal to 0 to 60 seconds. Now I have only up to 1 minute maximum limit I have. So T value varies from 0 to 60 seconds. Let's fix the n naught value. What is that? N naught. Maybe see the maximum count. What is that count we have over there? So now I'm taking barium atoms. No barriers. No barriers. Start counting. Okay, show time. It's okay. So I started lately. It's okay. But the counter stops after 1 minute. So you have to record this using Screencastify or AZ screen recorder. Okay. So 6,000 around is the maximum count. So fix that at around 6,000. 6,000. N naught is 6,000. And I'm entering my data. Whatever count. Count is equal to, I have to enter 60 numbers here now. Let's say initially for 1 second 15. Your data should be separated with comma. 15. So cumulative count, right? You're not counting for each second. You're adding up whatever data you are getting in. So 15, 35, 68, 128, 250, 500, so 580, 900, 1200. So like that, you have to enter 60 data points. So for the time being, I'm taking 5 data points. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'll take 10. 1200, 1600, 2400. So I took 10 data points. So now my n is n naught minus count. Right? N value is n naught minus count. So we have to get the expression for lambda and t half. That part we'll see. So for the timing, I'll plot the graph and see. So I'm removing these two. I'm placing a percentage symbol. T half and printing of T half excluded. And these two lines are excluded. So I'm taking figure, plot t comma n. I got data for t and n. If I run the program, what I get? Vector length mismatch. Okay. So I have to start from 1. I took only 10 data points. My timer is from 0 to 10 means 11 data points are there. So I'm changing it to 1 to 10. So error emochindi vector length must match and because my time data has 11 data points and n 10 points. So I changed the time data from 1 to 10. So you got some graph. I mean, if you take original readings, it should be exponentially falling curve. I mean, this should not be the curve. So you have to record the screen. I mean, you should get exponentially falling curve. So this data I have entered manually. You have to record the data and plot the graph. So what you have to do? N naught by 2. So let's say you're taking 5917 is the maximum number, N naught by 2, half of it, around 2998. You have to mark that N naught by 2 and from there you have to calculate T half. So at that N naught by 2, if you plot a vertical line, you will get T half. So from there lambda can be calculated. Once you know the T half value, lambda can be calculated. So you have to write every equation in a reverse order. Right? So you can make all those small modifications. This will be your fourth experiment. So cyclotron, synchrocyclotron, GM counter, T half. 4 experiments are over. Do you need any break? Shall I continue? So do you need any break? For 5 minutes, if at all. So I have 4 more experiments, very short experiments, can be completed in the next 30 minutes. So we'll take 5 minutes break and continue. Okay. So we'll go to next experiment. So what is our next experiment? It is mass spectrometer. So the next experiment is mass spectrometer. Oh, so this one. There is a blog at the beginning. File could not be accessed. Mass spectrometer simulation. So one simulator is in this physics classroom app. Okay. So mass spectrometer. There are two simulations, one from physicsclassroom.com, another is this one, German website. Okay, the one we have used already for cyclotron. This is a cyclotron simulator. On the same page, you have mass spectrometer simulator also. I'll go for the third one, the King Center for Visualization Science. Google on search cheyamantadu. So to search on Google mass spectrometer simulation. Mass spectrometer simulation. um.es kada. jscloud.inf.ws. link live link ledante, that is expiring, that is why చూస్తా. Right. Magnetic field and electric field control. Right. So, okay, we are using the same link that were used for a cyclotron. ఈ cyclotron simulator లోనే mass spectrometer కూడా ఉందండి. Otherwise, I'll share the link. That is mass spectrometer simulation. Right. So here we are separating isotopes. So mass spectrometer is used to separate isotopes. Isotopes ante entandi? Elements with same atomic number but different mass number. Neutron number maatrame different ga untundi. Then how do they get affected by electric and magnetic field? Anyway, their mass is different. So neutron count change avutundi isotopes kabatti. So corresponding mass will change. So when we keep them in magnetic field, radius of the circle will change. If you keep it in perpendicular magnetic field, what was the equation? BVQ is equal to mv square by r. So based on mass, radius changes. Why? The reason so BVQ is mv square by r. So what is that? Right. So here initial velocity is constant, charge of the particles is constant because they are isotopes, number of protons is constant, magnetic field is also fixing. So initial velocity is constant, v is also constant. So m by r should remain constant. The more the mass, more is the radius, less the mass, less is the radius, so that the particles will get separated in the presence of perpendicular magnetic field. And the control parameter is mass of the particle. So what I am taking here, so the simulator consists of a set of samples, sample A, sample B, sample D, different samples are there. You can control the magnetic field initially just to select the particle beams. Let's say I have particle A, sample A. I'm applying magnetic field and I'm starting the simulation. They're going somewhere. So there is a window, narrow slit to the first chamber. So if I apply magnetic field alone, they are moving up. If I apply electric field, they'll start moving downwards. somehow you can control the particles. So the initial control is to select a particular mass of particle. I mean, if you have 2-3 different samples or mixture of particles, in the presence of magnetic field, they will change. So heavy mass will take longer radius, lower mass they'll take lower radius. So they'll get separated initially. And you are going to select only one beam to cross the slit using these two controls. Initial controls are to select one particular beam. Right? And after that, on the second portion, if you raise the magnetic field, the particles will take circular path. So you can measure the diameter or radius of the orbit in the second part, and from there you can calculate the mass of the particle. So from here you got diameter or radius of the path. From there you can get the mass of the particle. Okay, so you can ask ChatGPT for that. So I'm giving the simulation link. So my question is this: study the simulation and prepare a lab manual with aim, apparatus, formula, theory, procedure, table, precautions, result. For determining mass of isotopes using mass spectrometer simulation given above. So I gave my requirement: study the above simulation and prepare a lab manual with aim, apparatus, formula, theory, procedure, table, precautions, results. To determine the mass of isotopes using mass spectrometer simulation given above. Right. So it studied the page simulation clearly and it is giving us. So aim to determine the mass of isotopes using mass spectrometer simulation. Available at virtually experimental website. Computer with internet connection. Ivanni vachinai. Formula. So it's not visible. I'll refresh it. Formula కనబడటం లేదు. Meanwhile, I'll share the link on WhatsApp. Right. So from the last graph, what we are getting, radius of the orbit is fixed. We are getting that radius. B we are fixing in the second half. We have to consider the data from second half. So first half is only to select a particular beam out of the entire set. There are 2-3 particles. If there are 2-3 different kinds of masses mixed in that, first controls are to select one particular beam out of the mixer. Second part is the actual measurement part. So we are excluding other beams on a lower radius. We are selecting only a particular beam. And in the second part, we are using that BVQ is equal to m square by r. From there, we get r. So if you measure this, here it is 3 centimeters. 3 centimeters is the diameter. So 1.5 centimeters is the radius. R radius. M is unknown. V velocity can be calculated from initial setup. From the initial setup, you can calculate the velocity. You know the electric field, you know the magnetic field. Balancing those two equations, you can get the velocity of the particle from the first half. Then you get m value. V is fixed, charge is also fixed. Okay. See here, m is a BVQ by r. I mean QVR by V. Velocity can be obtained from E by V value. So E by V are the settings from first half. Second V is from the second half of the setting. Okay. So this is a lab manual, and you can calculate the mass of the particles that you are selecting. Right? Done. So next one. Okay. So next one I'm going for is alpha particle decay. So how many experiments completed as of now? 5. Next, alpha decay. Gamma theory of alpha decay. So here is the lab manual. So we are using Octave MATLAB code to simulate the alpha decay. So what is happening in alpha decay? Alpha particles are coming out of the nucleus even though they have less amount of energy. So here the nucleus is considered as a potential well, and its average height is around 30 MeV. But the alpha particle energy is around 4 MeV. So there comes the question, how these particles coming out of that very high barrier. So here we are trying to simulate that and confirm that particles are tunneling through the barrier. Tunneling అనే ఒక యాక్టివిటీ జరుగుతుంది. దానివల్ల particles బయటకు వచ్చేస్తున్నాయి even though their energy is less than the height of the barrier. So we are using the equations. So this is the potential I'm considering, Coulomb potential 1 by 4 pi epsilon naught Z square by R. So the potential depends on R, means from the center of the nucleus for a fixed value of radius throughout a particular distance, the potential remains constant. So I'm considering a spherical potential. So if I draw a graph between radius and energy of the particle, we'll see that. So I'm considering a spherical potential, and if you calculate the tunneling probability, you'll get 2 pi e power minus 2 pi Z square by hv. V is the velocity of the alpha particle, h bar Planck's constant by 2 pi. That is the atomic number. E is charge of electron. Okay. Decay constant. F is the frequency of alpha particle collisions. T half-life. So this is the theory of alpha particle decay, Gamo's theory of alpha particles. And I got the MATLAB code for that. And I try to incorporate with the plot. So what was the question that I have asked? Add a plot for potential well and alpha particle wave function during the tunneling. సో టన్నలింగ్ జరిగేటప్పుడు ఆ పార్టికల్ వేవ్ ఫంక్షన్ వీటిని కూడా ప్లాట్ లో ఇంక్లూడ్ చేయండి అని చెప్తున్నాను. సో ఐఎమ్ గోయింగ్ ఫర్ పంపించాలి కదా. దిస్ ఈస్ ద కోడ్. MATLAB code shared on WhatsApp, and I'm pasting the code into online Octave compiler. So we run it. Error y-axis. Okay, there are some modifications. So I need to use that Octave GUI. Where is this Octave GUI? Okay, got it. Okay. So this is a Windows installer, Octave. So Octave, there is an app for Android version also, but it is 180 rupees cost. But there are some issues that it cannot run certain codes. Android version is not compatible. Android version is not compatible for certain functions. So yeah, Gamma theory. So I'm defining all the constants: E, H bar, C, epsilon naught, atomic mass units, MeV to joules conversion factor, Z, A, E alpha. So I'm taking energy of alpha particles as 4.2 MeV. Energy of alpha particles in MeV. E alpha is 4.2 MeV. M alpha is 4 atomic units. That means alpha particles, 4 atomic units. Radius of the nucleus is 1.2 A power 1 by 3. So A is the atomic number, 238, uranium. So radius is proportional to 1/3 power of mass number, because volume is proportional to mass number. So radius, that one. Next, I'm defining the potential, Coulomb potential 1 by 4 pi epsilon naught Z square by R. Same Coulomb potential. And further, I'm converting this into joules, MeV to joules conversion factor. Then I'm calculating the tunneling probability. So E alpha J is, energy of alpha particle also I'm converting into joules, MeV to joules. So if E alpha is less than Vc, so Coulomb potential kanna alpha particle అనేది తక్కువగా ఉంది. What happens? So after all the theory and equations, so A is equal to radius of the nucleus, V is Z square by 4 pi epsilon naught. So I'm calculating the tunneling probability. T is equal to e power minus that gamma integral. What is that tunneling probability? So tunneling probability is given by Z square by E square HV. Decay constant is F times P. F is the frequency. Okay, I mean whatever there in the theory, I'm placing it into a program. So I'm able to calculate T half. Then barrier height, I'm printing the barrier height, which is Vc, Coulomb potential value. And then gamma integral, tunneling probability, decay constant, and half-life. So if you run this code, right. So this is the data I'm getting as output. So Coulomb barrier height is 17 MeV. Gamma integral is 3.29. Decay constant 9.57 into 10 power 20 per second. Those many disintegrations per second. Half-life 7.2. So we have considered the energy of alpha particle is 4.2 MeV, and here the height of the barrier is 17 MeV. Still, the tunneling probability is 1. So 100% the particle is coming out of the barrier. So if you add the function for plotting, so I have to take the last one. C. So this is the last program. So I mean there is one more experiment. So this is the Coulomb potential. The red one is the Coulomb potential. Blue one is the wave function of the alpha particle. So it is tunneling at this height. So it is coming out of the well at very lower heights at around 4 MeV. The height of the potential is 17 MeV. The maximum scale is 20. Height of the potential is 17 MeV, and the particle is coming out of the box even though it has 4 MeV of energy. So this is the wave function of the particle. Okay. So with that, alpha decay is over, and I'll go to the last chapter where you will be analyzing PET scan data, PET scan, positron emission tomography, the applications of. Okay, so PET scan, positron emission tomography. So you'll get some kind of image, just like your X-ray data. You'll get a color image for the PET scan, and you have to analyze. Let's say I have the PET scan So this is the scan image of a human body. PT scan. This is head, spinal cord, back, side view, front view. Some random image. So the red spots are actually cancerous cells or whatever, wherever that PT scan is active. I mean, these are the locations we need to identify and send our drug. Okay. So we have to identify these locations using a program, mark those locations using a program, and send it to the drug delivering machine. Then the drug delivering machine will release the drug at those particular locations. Right? So we need to analyze this PT scan image. Here we have color image. So we have to convert that into grayscale image. And based on the threshold of that grayscale means all colors will be now between 0 to 1. Complete the black to white. That's called grayscale. So you'll get a grayscale image, and based on the threshold and intensity of the gray colors, you can identify the particular location of tumor and mark it. So that is the job we are going to do here. So there is a MATLAB or Octave code for that. So for the online compiler, you cannot give input image. So you need offline compiler. So this is the image PET scan to.jpg. That is the image I'm considering here. PET scan to.jpg. So your program also should be in the same location where the image is placed. So you have to give the name of the image. Then what is it doing? IM show PET image. So it is showing the original image that you are sending to the program. It shows the original image. If the original image is tricolor, RBG combination, if it is color image, convert into RBG to gray. Convert the color of the image from RBG, red, blue, green combinations to gray color. Then show the image again. Right? So original grayscale image. So this one is the original color image. If it is grayscale, if it is color, we are converting it to grayscale and then showing the image. Next, what are we doing? We are filtering the image using a Gaussian function. What is Gaussian function? This is the most standard function for every activity in nature. Let's say there are 100 students in a classroom. 60 will be in average band, 20 will be in below average, 20 will be average. So whatever activity in nature will be behaving like a Gaussian function. So we are applying that Gaussian filter to the given image so that the image pixels also behave like the natural activity. Okay. Right. So I'm using a Gaussian filter so that the image also behaves like natural data will be available once I filter it with it. All noises, everything nonsense will be filtered out and we get original image data. Then I'm converting this to, now I'm applying a threshold. Threshold value is 125. So I'm trying to collect the tumor location. So by varying the threshold, you can mark the tumor precisely. Then I'm using square, or you can use disc also. What type of circle or a square or disc, whatever you want to use, you can mark the identified location. So if you are using circles, it's okay. I'll run the program and show you. Then I'll explain it. Right. So this is my original image, color image. Then I have converted it into grayscale image. Then I am fixing a threshold value. My threshold is set at 125. 125. I will vary it and see how it is changing. Then I am circling the identified regions with a disc shape pattern. We can change it to square also. We'll see that. And I'm defining the size of the disc. Then PW label. I'm labeling them with the size of the circle. So I'm drawing circles around the identified regions. Then I'm labeling. What is that I'm labeling? With the area. Area, center of the circle, and bounding box. With this information, I am labeling the circled regions. So that is the final image. So what is that final image you got? Here is, this is the final image you got. All the regions with the cancer cells are identified. They are marked with the size of the area. Area is 36, area is 56. It's like that. So if I change the threshold value, I'll get more and more data. Let's say if I change it to 150. Let's say if I change it to 150. Original image, grayscale image, nothing is identified. So if I reduce the threshold means what? So if I reduce the threshold, I change it to 100. So now I got more and more points coming into the observation field. So by changing the threshold, you can precisely identify the location of the cancer cell. That's all. So this program runs in Octave, and you have to supply the PET scan image as input. Done. So with that, I'm closing the session with 7 simulation experiments on nuclear physics. Done.